Hello and welcome. Today we're going to talk about section 4.2, and because everyone's sort of at a different place, all the classes, we'll just go ahead and start from the beginning. So this is section 4.2 in our course manual. It's on annuities, and the goal is to understand the computations and concepts required in lending and borrowing monetary values. So the first important point is to understand what an annuity is. So I'm going to jump over here, and we'll define annuity. An annuity is simply an investment with regular and reoccurring, I might misspell this, so I apologize, reoccurring, that looks okay, reoccurring deposits. Sometimes these deposits are just referred to as payments. And for our sake, we'll just abbreviate this PMT. So these are payments that you're making at regular intervals, and you're making them over and over again. Some examples that we'd think about would be 401k. 401k is a tax code, and 401k is specifically for nonprofit organizations, and this could include government and other charities and things like that. So this is a retirement plan. If you work for this is 403b would be that. A 401k is a private sector employer retirement plan. So if you have a company that you work for full time, then they might offer you a 401k, and usually the benefits are that they match what you invest at some percentage. So maybe the employer will put in 5% of whatever you put in, up to a certain limit. Then if you don't work for a company, or your company doesn't offer anything, you can actually open an IRA, which is individual retirement account. And this is basically, anyone can open this. Usually there's a cap on how much you can put in every year, and usually you can't withdraw for a certain period of time. So they all have their own rules and regulations, but these are just three types. So this is 403b is nonprofit. 401k is private sector, and IRA is individual retirement account. Usually we say IRA or IRA. Okay, so basically these are recurring payments. So I'm going to jump over to a page within our course manual. This is page 170, and here we have a visualization of a time diagram in which, let's suppose you decide to put away $100 for each of the next 12 months, at which time you'll take that money to make a purchase. Additionally, suppose that you find a rate of 12% compounded monthly. The time diagram will look like this. So basically, we see these different $100 increments coming in every single month. And this is a regular, reoccurring $100 payment. Regular in that it's a fixed value. You don't have to have fixed value annuities. You can have variable annuities. These get a little bit more complicated from the math standpoint. So let's take a look at an example. Suppose you put away $100 of your monthly paycheck into an annuity that pays 12% compounded monthly. What will you have saved up in 3 months with interest? Don't attempt to use TVM Solver yet. Okay, well, this means now normally I'd kind of want you to think about this as to how this works. But if I put away $100, we'll look at the month, then we'll look at the beginning balance. Then we'll look at the interest earned, and then we'll look at the payment, and then we'll look at the ending balance for that particular month. So we always call it month 0 because that's sort of the initial starting time, and it does actually count as a month. It's not just like no month. It's month 0. It's the beginning month. So initially we don't have anything in there, so we're not going to earn any interest for that month. This is why in our calculator in TVM Solver we have PMT. A few people asked. We have this set to end. It's not that you can't make investments at the beginning of the month, but typically the way things work out is that interest is paid after you've left something in there for a month anyhow. So it's just easier to get on the end of the month bandwagon. Okay, well then you add a $100 payment, and so your ending balance at the end of the initial month is $100. So you haven't earned anything, but 1 month has passed by. Now, the next month, so 1 month later, your beginning balance is 100. Now, it's 12% compounded monthly, so that means you earn 1% a month. And that means that your interest, excuse me, we're just looking for the interest portion, so this is going to be $1. Okay, so that means you're going to input another payment of $100, but now you have $100 plus your $1 plus your beginning balance, so you have $201 in your bank account. Now the second complete month comes around, and now your beginning balance is 201. So you get 1%, because this is compound interest. You get 1% of that, which is $2.01. You make a $100 deposit, and now you have, well, you have your 100 plus your 201, $2.01 plus your $201 beginning balance. So you have 303.01. And this is the way it works on and on and on. Now, I'm trying to jump to the next page here. Hopefully this will let me. I'm trying to do this. Sometimes this thing gets a little tricky. There we go. That's what I'm looking for. So the next page, well, what's happening here? How does this work in terms of compound interest? In terms of our compound interest formula. So how does this come into play? 1 plus r over n times t power. Okay, so this is the total number. This is in our calculator what we refer to as n. This is what we sometimes refer to as I. We have to take the APR divided by the number of times we compound each year, and so we've seen it a couple of different ways perhaps. Okay, well, your total ending balance after 3 months will be, now your initial $100, that will earn, if you leave it in there for 3 months, that will only earn interest twice. It'll earn interest here once, and then aggregated here, it'll also earn interest once here. So your first $100 will earn 1% interest 2 times. Now, we have to add to that what your second payment becomes. Now, even though these are aggregated together as ending balances, we can treat them as separate numbers. We'll see that we still get 303.01. So now you make your next $100 payment, and that earns interest exactly 1 time because it's only left in there for 1 full month. So you have another $100 payment, and that's paid 1% for 1 month. Okay, so this is payment 1, payment 2, and then we'll do payment 3. And your third payment, because it's actually in there, that's the last month of investing, that earns interest 0 times. And notice that that was in fact the case, that this guy did not earn earn any interest at all. It just became part of the ending balance. So now what we see is that we have basically this descending order of powers. And we see that there's a very straightforward pattern here. Now, if we actually calculate this, we come over to our calculator and just type this sucker in, 100 times 1.01 squared plus 100 times 1.01 first plus 100. Lo and behold, we get 303.01, which is exactly what we got by doing it the table way. So we can see that it doesn't matter whether we treat the payments as being separate or treat them as being one, we end up still getting the same answer. And so whenever you might notice that whenever you repeat this, like let's say you did this for a full year. If you did this for a full year, you'd have all these $100 payments, and of course now because your first payment is made at the end of the 0 month, that payment's only going to earn interest 11 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times to get to month 12. Now, in this descending order, every payment is going to earn 1 month less worth of interest. So basically, these are all the individual balances. $111.57 is what your first payment will be worth in 1 year. And so these numbers kind of get smaller because each $100 earns interest for a shorter period of time. So this is kind of a pain if you think about it. Gosh, we have to add all these terms up. And now imagine that you're looking at some investment 30, 40 years down the line. So here's what we kind of observe. We'd have to add up all these guys. There is a trick here. So mathematicians realize, hey, there's got to be an easier way to do this. So one trick that I wouldn't expect you to know, but that works out quite well, is just to take this and think about it as an equation. Multiply both sides by the growth factor, which is 1.01. So you get 1.01a equals 1.01 times this side. You distribute that through, so you get basically all that happens to each of these terms is that the power goes up by 1. So 1.01 times 100 times 1.01 to the 11th becomes 100 times 1.01 to the 12th, and all these in descending order. Now notice that we get a bunch of similar terms now. So this guy matches up, this guy matches up, this guy matches up. They all match up except the last two terms, except this guy here. Except the 12th power guy doesn't have anything to match up with over here, and the 0th power guy doesn't have anything to match up with over here. So if we actually subtract these two equations, 1.01a minus a, everything cancels out except the very largest term and the very, very smallest term. And now if you reduce this down, 1.01 minus 1 is 0.01, a equals that, and then you divide by 0.01, you get this thing here. Well, that looks a lot simpler. And we come to our formula, which is also in the PowerPoint here. It's this formula here. We actually notice that our payment is 100. That shows up in the front. 1.01 raised to the 12th power. Well, hey, that's the total number of months of the investment. Subtract away 1, because actually you can simplify this by factoring out 100. And 0.01, that's just our APR divided by the number of times we get interest every year. So this formula actually generically works. We just kind of, based on the pattern, observe that it reduces down to this. And this will work all the time. So here's the formula we can use. Now I'll let you verify if you'd like to see that based on this problem here, that you still get 30301 when you plug in 3 months. Well, I guess I can show you how to do this. No rush, right? So 100 is our payment. If you want, you can put the whole numerator in parentheses. 1.01 is our rate divided by our number of compounding periods in a year, raised to the 3 power because we're compounding 12 times, but we're only going for a fourth of a year, minus 1 divided by the rate divided by the number of compounding periods in a year, 0.01, and we get 30301. So we basically have 3 techniques of doing this. The first technique is by just doing it the old-fashioned table way. The second technique is to actually just add up the terms individually, and the third way is to actually use this formula. In the TVM solver, this is actually not very difficult to do either. In the TVM solver, all we need is to input things the same way we would. So if I'm looking at 3 months, and I'm compounding monthly, at an interest rate of, well, this is APR, so we've got to input 12% here. That's our annual rate, compounded monthly. By present value, because I'm actually not putting any lump sum of money in, I'm making a regular payment, this will be 0. You might say, well, why not 100? Well, the 100 is a regular payment, and that goes right here. So I'll put it as negative 100 because assuming that I'm investing, I'm outflowing $100 every month. And this $100 goes into effect this many times. Every time a compounding period takes place, a payment is assumed to be made. So now I can come over here and calculate my future value, and I get 30301. So just as simple as that. Now let's say you put in a $5,000 lump sum, like you just had $5,000 lying around. Then you would also make this negative 5,000 if you were making a one-time deposit. For the sake of making sure this video doesn't get too extraordinarily long, I'm going to stop it and record a part 2, and we will see you back in a minute.